Hello everyone. Today we are doing section 7.8, repeated roots or repeated roots of like characteristic equation or repeated eigenvalues. I don't want to do the standard lecture because linear algebra requires lots of calculations and writing, but not that many ideas which we are going to use. So what I'm going to do, I'm going to use make it clear. I'm going to use my notes, and I'm going to highlight major ideas here. So, well, remember in the previous lecture we were talking about systems of equations, and we know that we're supposed to find eigenvectors and eigenvalues of a matrix A, which is like matrix of the right side, right? Now we know that solutions are going to be a standard solutions when we do have real different roots of this characteristic equation, which is produced by determinant of this matrix. But what is going to happen if a couple of these values are repeated or more than two? Usually we are going to deal with 2 by 2 systems, but who knows? What we will do in the second order equation when we have a repeated root. Well, remember that when you have a repeated root, it's going to produce two same functions as solutions, right? And we cannot use the two same functions as solutions because they are linearly dependent. So we are multiplying our function by t to find linearly independent solution of our equation. And because it's a second order equation, we need two linearly independent solutions, and one of them is a standard solution, which is produced by characteristic equation exponential, and one of them is going to be solution with multiplied by t, right? So what is going to happen with systems? Well, what I have over here, I just took my second order equation and converted it into a system. I set up x1 equals to y, and x2 equals to y prime. Then second derivative of y is x2 prime, right? Then minus x2, which is first derivative, plus x1. And I have also a second equation, which is produced by derivative x1 prime. If we differentiate x1, that's going to be same as we differentiate y, so we are going to get y prime, right? And y prime is actually x2. So that's going to be our somehow I cannot erase anything already. Well, that's fine. So we get a system of two equations. Basically, guys, you understand, solution must be same no matter how we solve it as a second order equation or as a system. But we can kind of maybe using these ideas develop a method. Well, a standard system is going to look like x prime equals matrix of like coefficients multiplied by x, right? And we set up determinant to find eigenvalues. Determinant, we set up determinant, and determinant is going to produce characteristic equation, which is going to be exactly the same characteristic equation we had for second order equations. So it's r minus 1 squared, which is going to produce two exactly same roots, 1 and 1, right? We start solving for the first root, which is 1, right? And we find that my eigenvector is 1, 1, right? And I multiply by exponential factor and by a constant, and I got my first eigenvector. I'll need the second one because system of two equations, right? So I'm moving over here and I continue. So why don't we just multiply this eigenvector by t like we did in the previous one, right? We did it over here. Why don't we just multiply it by t, and that's going to produce a solution? Well, yes, it's going to produce a solution actually, which is absolutely correct. But let's see what side effects is going to have this solution. If we multiply x1 by t, we are going to have a solution which is going to be t exponential factor by vector 1, 1, right? If we differentiate this solution, constant and the vector are going to stay as they are. They are just constants. But exponential factor multiplied by t is going to produce two terms, t e to the power of t and e to the power of t, like a product, you know. You differentiate for exponential factor and then you differentiate t. T derivative of t is 1, so we are going to have two terms. If we plug them in back into our equation as a derivative, we are going to see that on the right side, we don't have two terms. We're just going to have one, which corresponds actually to the solution of t e to the power of t, right? Why actually the sum of these two terms is going to be not the sum, but these two terms are equal to each other? Well, if we cancel out t here and we cancel out exponential factor, we're actually going to have equation a minus r I, and 1 is eigenvector, so means that it's a solution actually, so it turns this system into a true statement. That's why these two terms are equal to each other. But we do have a leftover term, which is going to have nothing over here corresponding to him. Let me make it a little bit narrower. It's too wide. I think this one is gonna be good. Okay, so what should we do? Well, remember how we were doing non-homogeneous equations and how we were trying to guess what is going to happen? Well, what we can do in this case, we can adjust actually this term by adding something to this solution, right? We already have a term with multiplication. Let's add actually just term looking like this, but with arbitrary constants. So why? Well, because over here you see it's e to the power of t is going to be multiplied by the vector 1, 1 here. So, well, e to the power of t is a function, so we need to have e to the power of t on this side. Vector is going to be different probably because we do have some stuff from the matrix, because matrix is going to be multiplied by this thing too. So what we are going to have, we are going to add something, and this something is going to be exponential function multiplied by unknown vector AB, which we are going to determine by substitution back into equation and finding out A and B constants. And what I did, well, I'm skipping writing down the constant C2 over here. I'm just writing down the vector as proportional to this expression. Now, because I have two different terms, one of them is going to be differentiated and is going to give me t to the power of t plus e to the power of t, as it was given before. The second one, you differentiate it, it's still e to the power of t, just because you differentiate e to the power of t constant is going to stay as it was. We plug in this derivative into equation. So this is actually, what is this? This is my x prime, right? And here we do have our matrix, and we do have over here x. It consists out of, well, the term which we produced by multiplying by t and this strange term which we add, which I called something. Now we are going to eliminate two terms which are solving equation, and they are going to be the term with t here and the term with t here. Well, yeah, the term with t is going to be multiplied by the matrix here, but again, the vector 1, 1 is a solution actually of A minus Ri matrix. So they are going to cancel. What we are going to have that's left over, two terms on this side and one term here. And I'm going to just copy leftover terms, leftover from the first expression, leftover from the second expression, and leftover from the last expression. Last expression, which is on the right, is going to be also multiplied by the matrix. Which matrix? Let me show it. The matrix which we have over here, minus 1, 1, minus 1, 1. Oh, no, maybe not. Sorry. That was already modified matrix. The matrix is 0, 1, minus 1, 2. That's the matrix we are going to have instead of A here. And because we have exponential factor repeated in all the terms and it's never equal to 0, we're just going to divide by it and cancel it, right? On the left side, we have the sum of two vectors, 1, 1 and AB. I'm going to write down as a sum. That's just like x component and y component, or you can like first component, second component. On the right side, we have a product of the matrix by a vector AB, which is unknown. I'm going to multiply my matrix A, which is 0, 1, minus 1, 2, by my vector AB. And it's going to produce a vector again, b minus a plus 2b. I did a multiplication, so trust me, maybe I did a mistake, but that's not essential here. Essential is to understand how it works. Now I'm simplifying this. So on this side I have 1 plus a, on this side I have b. So it's 1 plus a equals b. I write it down as an equation. 1 plus b, and on this side minus a plus 2b, another equation. So two equations, two variables, I can find them. And I see that these two equations are actually same. So my first equation and my second equation are same. If I simplify my second equation, I'm going to get exactly the same value. So actually I'm going to have a free parameter. I'm going to call this free parameter a, and I'm going to solve for b. B is going to be equal 1 plus a. That's my free parameter a. And my final solution for a and b is going to be a 1 plus a, where a is going to be here arbitrary constant, so you can take any number for a. Now I'm going to combine these two solutions together. So first comes my solution multiplied by t, and second comes my solution which I just found. What I'm going to do with this solution, I'm going to simplify it a little bit. I see like a, and a plus 1, right? I'm going to represent it as a sum of two vectors. My first vector is going to be a, 1, 1, and my second is 0, 1. If you add these two vectors together and multiply a by 1 and 1, like, when you have a coefficient, you multiply by every term in a vector, you are going to get the same, a plus 1. Why I'm kind of separating them? Because when I multiply C2 by each of these terms, I am going to find out that C2 by the first term is going to give me this. C2 by the last term is going to give me this expression. And C2 by the middle term is going to give me C2, which is arbitrary constant, right? By arbitrary constant A, and by the vector 1, 1 and e to the power of t. If we recall, how was my x1 looking? It was looking like the constant y1 e to the power of t. It's exactly similar to it. Yes, it's not same, but it's proportional. These two things are linearly dependent. So we are going to drop this because we don't need linearly dependent vector here. Okay, and that's going to be our final solution. So final solution is going to look like this weird sum of a standard approach plus a thing. Okay, I'm going to put two solutions together. Solution x1, which I calculated in the beginning, plus solution x2, which I just calculated over here together. And you can simplify it or you can leave it as it is. There are two arbitrary constants because there are two linearly independent vectors. I'm suggesting you to solve at least one problem on your own because there are lots of steps and it's very easy to get lost, like forget, okay, what should I do next? Yeah, I don't remember. Make sure that you solve at least one problem. I'm asking you to solve two problems for the homework, but make sure that you solve at least one of them, okay? And next section which we are going to cover is section 7.9. I kind of going to explain in the same lecture because I'm not kind of writing down everything, so it's going to be much faster. So non-homogeneous linear systems. Well, non-homogeneous linear systems are going to look like equation which you see written, right? That's x prime equals p of t, the matrix of coefficients. I don't know how to write down matrix manually. In the book, they just make it bold, right? Multiplied by the vector of unknown functions and non-homogeneous part, g of t. G of t can be sum of several vectors. And let's consider example. I'm using system x1 prime equals minus 2x1 plus x2 plus 2 e to the power of t, and x2 equals x2 prime equals x1 minus 2x2 plus 3t. I'm going to write it on the standard form. So first, this one is going to make up vector of derivatives, right? So this one is producing x prime. And this one is going to produce a matrix of coefficients minus 2, 1, 1, minus 2 multiplied by a vector of solutions, x1, x2, right? Solutions are x1, x2. What I'm going to do with leftover coefficients, terms which are actually my non-homogeneous part, I'm going to represent them as two vectors. Why? Because they are essentially different functions. This is exponential function, and this is polynomial. So I'm not planning to solve them at the same time together. I'm planning to solve them separately. So I put exponential functions separately from polynomial. So they are making g of t, but I'm kind of separating them into g1 of t and g2 of t. Now, as usual, I solve homogeneous system. I found solutions. Here I was lucky and I got two real roots, which are distinct to real roots. So I have two like eigenvectors. And I find these eigenvectors. You can check me. Maybe I did a mistake somewhere, but I found that these eigenvectors are 1, -1, and 1, 1. And I multiply them by corresponding exponential factors. And that's my homogeneous solution. Now I'm going to use method of undetermined coefficients, which we developed in the second order equations, and solve non-homogeneous system. How I'm going to do it? Well, I'm going to look at my first function, exponential function, and see that exponential function, it's just the function multiplied by the vector with coefficients 2, 0. Well, how should I look for a solution? Well, I should look for a similar solution, exponential function and a vector with unknown coefficients. That's what I'm going to do. I'm going to set up unknown coefficients AB and exponential function, take this as my proposed solution, plug it into the equation, and actually calculate A and B. Well, I did the calculations and I got 1 over 4 for B and 3 over 4 for A. What I'm doing, guys, I don't like to write down fractions in the vector. I'm writing down 3 and 1 and divide over 4 the whole function e to the power of t. If you don't like it, you can keep 3 over 4 and 1 over 4. And maybe I did a mistake here, but I'm hoping that I did not do. Well, what should we do with my second function? Remember, we had two functions, exponential function and polynomial. We're going to do the same. Let's look at how polynomial function looks. So my polynomial function looks like I have a vector multiplied by t. So it's actually a first order polynomial. If you write it down in terms of vectors, it's going to be a t plus b, right? General polynomial of the first order. That's how I'm going to look for a solution. And I'm going to write it down like a1t plus b1 and a2t plus b2 to specify numbers here, because I'm going to search for these numbers, right? So I'm going to differentiate this. And when I differentiate, remember, differentiation is same for vectors as for just like functions. So constant is going to give me 0 and t is going to give me 1. So I'm going to just have a vector of a1, a2. So what I'm going to do, I'm going to plug this one and this one, the derivative, into the equation. Don't forget about the right side. And I'm not doing exponential part, which I already did. I'm writing down only polynomial part. So I'm solving and using superposition principle here. So I'm solving separately for different right parts or for different non-homogeneous functions. And it's kind of long, but I kind of simplified everything and I got two equations, but actually these are not two equations because each of these equations must be equal to 0, which means that coefficients of t is supposed to be equal to 0 and coefficients of t to the power of 0 is supposed to be equal to 0. So we do have t to the power of 0 in each equation and t in each equation. So we are going to actually produce 4 different equations here. I wrote over here for comparison polynomial. So I have 0 multiplied by t plus 0. So this 0 is matching the sum of these terms, and 0 multiplied by t is matching coefficient of t. So coefficient of t must be 0. So 2a1 minus a2 must be 0. And I'm writing down all these 4 equations separately. And I was very lucky. Systems of 4 equations are extremely long to solve, right? But I was very lucky. It looks like my system kind of has separately a1 and a2 in 2 equations, which I can solve separately and calculate actually that a1 is equal to 1 and a2 equals 2. Then I plug them back into equation number 1 and number 2. And I calculate b1 and b2. And they're not as nice as a1 and a2, but they're still not bad. They're like 4 over 5 and negative 3 over 5. I put everything back into my function and I got my second solution. Now I'm going to combine everything together, like my homogeneous solution plus my first solution plus my second solution, and write it down as a long expression. What I have over here is called the general solution, right? If somebody assigns you initial value problem, something like this, let me just make it very thing, like initial value problem. For example, if somebody tells you that x1 of 0 equals 1 and x2 of 0 equals 2, initial value problem. Somebody assigns initial value problem. How it's going to affect your solution? What you're going to do, guys, you're going to take this 0, which is t, plug it here, 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 plug it over here, plug it over here, plug 0 everywhere. And eventually you are going to have here like two lines with constants C1 and C2. And on this side you are going to have numbers 1 and 2. Using these numbers and these two equations for C1 and C2, you solve them. Students are always asking me, like, when do we plug it in? Do we plug it in when we find homogeneous solution? Do we plug in this? Or when we find general? We plug it in when we find general solution. So you find first general solution, then use initial conditions. I'm not going to use initial conditions here because it's going to make my lecture very long. So I'm just asking you to do at least one problem on your own at home, because again, it's a convoluted solution and you can just skip a couple of steps and it's going to go all wrong. And maybe you can find my mistakes too. Okay, so that's all for this lecture.